Well, thank you everyone for coming tonight to the Big Bang Energy Disruptions, brought to you by the MIT Enterprise Forum of the Northwest and the Washington Clean Technology Alliance. My name is Jimmy Gia, and I am the chair for the organization. We're an all-volunteer nonprofit organization, one of 28 chapters across the world, and we're dedicated to bringing technology programs to the various different organizations and areas that we're a part of. We're managed by Technology Review, which is an independent media company owned by MIT with a global readership of over 4 million. Let's take a quick poll. How many people are here for their first MIT Enterprise Forum event of the Northwest? Excellent, well, welcome. And I hope you continue to come back to our future programs. On December 12th, as you can see in your program notes, we have our Venture Lab series on war stories from Patrick Husting, on the extended results of a story of an entrepreneur from bootstrap to acquisition. And our next evening program is going to be in January, which is on the changing face of manufacturing. And so if you enjoy tonight's events, please consider becoming a volunteer, where you can help bring programs like this together that inspires, connects, and educates tomorrow's leaders. And so tonight's planning committee has worked for many months to be able to put this together. And if you can please stand when I call out your name, Kirby Bartholomew, Jeff Kanan, Jamie Wiegand, Jan Graylorn, David Mitchelltree, Jacqueline Bean, Vicki Owens, Andy Silber, and Renee Gastineau. Join me in thanking them for their dedication. Come on, stand up, guys. Thank you very much. And none of our events would be possible without our season sponsors, and they are Firmer Lawrence and Haug, Equinix, Point B, and the Summit Law Group. And so without further ado, please join me in welcoming our moderator, Tom Rankin, for tonight. Tom Rankin is the lead guitar player for the new Johnny Bravo rock band, playing all of your favorite classic hits from the 50s to the 80s. And in his spare time, he is the president and CEO of the Washington Clean Technology Alliance. So please, let's give him a warm welcome.
Yeah, we'll be playing at Pogies in West Seattle on December 14th. You're all welcome. If you could like us on Facebook, that'd be even greater. So thank you and good night. These are your notes, right? So very few people know that Jimmy actually is a musician as well. He plays some sort of small stringed instrument. It's not clear what it is. It's a mandolin or a violin or a ukulele, but every time I talk to him, it's different, so I don't know. You know, one thing I hate about Seattle panel presentations is everybody is too nice. So we've had several meetings tonight, before tonight, to make sure nobody is nice to each other. And in fact, I've encouraged them to use the phrase, "Jane, you ignorant slut." Now, I don't know if they're going to follow instructions, but you notice that we did fill all their glasses with wine. They continue to drink, which is a good thing. I've got candy up here to get them juiced up on candy. If anybody sees an empty glass, please fill it up for us. So a word about the Washington Clean Technology Alliance. We're a trade association. We have 228 corporate members. We're focused on helping our members become successful. We're now the largest, at least of all the trade associations we know about in clean tech, we're the largest state-based clean tech trade association in the nation. And we work on advocacy, helping our members network, providing information about the industry, offering business services to our members, and connecting our members. So much for the advertisement. So a big bang in energy, I believe, is absolutely inevitable. So we have some terrific experts here, and with each glass of wine, they get better and better. And they have very widely diversified interests and backgrounds, which I think will help all of us learn more about what's going on. Nick Toren, Nick, well done, is reactor physicist at Bellevue-based TerraPower. TerraPower aims to develop a sustainable and economic nuclear energy technology, and that's funded in part by Bill Gates, I believe. Tom Nugent, nice wave. He's president and co-founder of LaserMotive, a very interesting company. They are a Seattle-based company developing wireless power delivery systems using laser beams to transmit electricity for applications where wires are either cost prohibitive or physically impractical. And Rob Pratt, he'd be the last guy down there. He's the manager of the GridWise program for the U.S. Department of Energy at the Pacific Northwest National Laboratory in Richland, Washington. That, as you know, is one of the 10 U.S. Department of Energy national laboratories managed by DOE's Office of Science. So this is an extremely complex topic with many, many different interacting aspects, but let me try to frame this with a couple of brief comments. First of all, we agreed in advance that there would be no PowerPoints whatsoever. So we found, yeah, it's good. Thank you very much. It's kind of a cheap applause, but I'll take it. However, we didn't say anything about paper. So I want to start off with a couple of paper slides. What do you mean, oh no? It's perfectly legal. I made up the rules. So this is, as you can see, U.S. population growth. In this last 60 years, our population has grown over twofold. Okay? This is energy utilization. Our energy has grown threefold. 2 times population, threefold energy. And this is energy use per capita. I'll clean this up later, guys. So. Show it over here too. You guys know this, don't you? So there was a lot of growth in energy, as you can see, up until 1970, right? And then all of a sudden there were the 2 oil shocks, and there were big drops in energy utilization in the 1970s. And then it gets pretty flat for quite a while. And then in the mid-90s, it starts dropping quite considerably. Okay, so this isn't economic necessarily. You know, the economy was going up and down. You see less energy utilization. And there's really a great story behind that. This is our energy utilization. You can all see this very clearly. I can tell in the back row that your Max Witter knows perfect. This is really amazing. This is, what is this? This is energy used per unit of GDP, right? So every dollar we generate in the economy takes a lot less. In fact, we use about 40% of the energy today to create a unit of GDP than we did in 1940. So that's really great work that's been done in terms of being more efficient with energy. Unfortunately, we're not the entire world. So this chart here is population in India and China over the course of the last 30 years. And as you know, that's not the entire story. Not only has the population been going up quite considerably, but they're moving to urban centers. They're moving from a third world, in some cases very poor, rural kind of lifestyle, to a lifestyle where they want to be urban and middle class. And it's working all over the world. And what that means is an explosion in energy utilization. To some degree, what we do certainly matters, but what they do really, really matters. So it's going to affect the entire globe. Will almost certainly have dramatic implications on living standards, both ours and theirs, world peace, global pollution and health, and the climate of the world. Some of these implications are probably inevitable. But there can be little doubt that technology developments in our country and around the world will be our best bets to deal with these problems. So I want to begin the discussion with 2 questions. I'm going to ask one question for all 3 panelists, and they're going to take 5 to 10 minutes to talk about it, and then I'll have a second question. So the first one is, this is a little redundant. So I would like to begin with a couple of questions that will frame the perspective. Hey, this is a serious topic. Can you tell us about yourself? Why are you here? What is your background and expertise? What is your organization working on? What's your role? And why is it important? Tara Powell.
Thanks, Tom. Good evening. So happy to be here on the panel. Thanks, everyone, for coming. Thanks, Tom, for the great introduction. That basically answers why it's important already. So, I'm happy to be here talking about my favorite topic, which, of course, is energy. I got interested in energy, as a kid when I was sitting around with some of my friends trying to decide, what we were going to do with our lives. We decided energy was going to be a big issue coming up pretty soon. And so we decided that the 3 of us were going to solve the energy problem. And so I naively went off to engineering school and happened upon an introductory nuclear engineering class, which I had never heard of course, and didn't think it was a good idea. But I took the class anyway on a whim. And as I started learning about it, I realized that this is it. This is how I can have an impact and really help the world with its energy problem. So that's obviously kind of a controversial statement right now, but I'm happy to defend it in the Q&A. But yeah, so the more I learned about it, the more excited I became. There's the regular reactors, which are actually pretty good in lieu of the bad things that you've heard about them. But then there's also this whole field of advanced reactors, which are all these different types of concepts, different ways to split the incredible amount of energy in the atom in ways that are even better than the technology that's currently in use. And so I became very interested in these types of reactors and started focusing my studies and research on advanced nuclear reactors. And my colleagues thought, okay, that's kind of a dubious choice. Like, why would you study things that there aren't any of now? Where are you going to work? What are you going to do? But I, stayed the course because I thought that if I really wanted to make a big impact that I was interested in making, I would have to go to advanced reactors instead of just the good enough reactors that we have operating today. And fortunately, I wasn't the only one who came to that conclusion. And around the same time, a man named Bill Gates decided that advanced nuclear reactors were going to be an essential part of the energy mix. And so he formed the group that eventually became TerraPower over in Bellevue, where I now am. So the fact that I was one of the few people who study these types of reactors, and the fact that they were one of the few places that employed people who study these reactors.
Worked out kind of nice.
Yeah, the connection was clear. And so I didn't have any trouble finding my way to Bellevue, where I've been for 4.5 years working on their projects, which I'll now tell you about. So what's TerraPower doing? The mainline development there is something called the traveling wave reactor, which is an advanced nuclear reactor that I'll go through. There are a bunch of other even more out there projects that people are working on, but it's kind of a 10%, 90% level. So we have very innovative things going on, and then we have this advanced reactor, the traveling wave reactor. So what is that? The traveling wave reactor is a type of advanced nuclear reactor that falls under the broad category of a sodium-cooled fast reactor. And that, I'll go through what all those words mean. Any reactor is just an arrangement of fuel that can sustain a chain reaction. And as the atoms split, they release energy and the fuel heats up. And so you have to pass a coolant by and keep the temperatures constant, move the heat over to a turbine of some sort. So any normal reactor that you see around here or anywhere in the world is almost definitely going to be cooled with tap water, regular old high pressure or high temperature water. And that's called a light water reactor. But a sodium cooled reactor is actually cooled with liquid metal sodium instead of water. Any eyebrows raising? So anyone, there they are. So liquid metal sodium, if you've taken a chemistry class, has a reputation for being highly chemically reactive, and that's definitely true, and that is a disadvantage of it. But the advantages actually far outweigh that. It's an unbelievably good coolant. It's a liquid metal, so it has very high thermal conductivity. It has very low melting points, so you can actually run your reactor without pressurizing it, and that's a huge deal in terms of safety, because if you have a very pressurized water reactor and you get a leak somewhere in one of your pipes, all that water has the pressure to push itself out that leak wherever it may be. That leaves your fuel without any coolant and can melt the fuel, which would then release the radiation, which is what you try not to do when you're designing a nuclear reactor. So a sodium-cooled reactor, because it has such a high melting point, has no pressure in the system. So if you get a leak somewhere, none of your coolant, which is surrounding your reactor, is going to shoot out there. It just sits there and keeps churning around. And furthermore, because it has such great thermal conductivity, it can actually cool the reactor without any external power whatsoever. So in Fukushima, they got into trouble because they lost their backup diesels when the tsunami wiped out their gas supply. And so they couldn't pump water around to cool the reactor. But in a sodium-cooled reactor, you don't need any of those systems. The whole power can go out in the whole world, and that reactor will sit there and naturally circulate, dumping its heat to the atmosphere without any trouble. And this has actually been demonstrated in actual test reactors in Idaho in 1986. Excuse me. So that's sodium-cooled. So now let's talk about what a sodium-cooled fast reactor is. And that just means the neutrons are going faster than they are in a regular reactor. When you cool your reactor with hydrogen, the neutrons hit the hydrogen. It's just like a billiard ball hitting another billiard ball because they're about the same weight. The neutron can slow all the way down. But if you get rid of that hydrogen that's in the water and put in sodium, then it's like a billiard ball hitting a bowling ball. It bounces right off and keeps its high speed. So you get this large population of high-speed neutrons. And what that does is, as the physics has it, fast neutrons are substantially more efficient at releasing energy out of mined resources. So to put a number on it, if you dig up a ton of uranium and enrich it and then put it in a regular reactor, you're going to get about 0.5% of the energy out of that as heat. But if you use a fast reactor, you can get 90% of the energy. So you get about 200 times more energy out. And that has huge implications in terms of footprint of the system. You have much less mining, you have much less waste, you have 200 times less waste per energy produced, you have less transportation of things, and you get much more energy out of your known resources. So it's sustainable. So any fast reactor is sustainable, is more sustainable, safer, and makes less waste and requires less resources. So that's the advantage of a regular fast reactor. And the traveling wave reactor is a twist on that, because in a regular fast reactor, you have to all the time be taking the fuel out and putting it in a chemical separation plant where you split it up into its constituents and bring and refabricate the good stuff into new fuel and take the waste out. And so you're kind of constantly passing it back to this chemical plant. But you've already split all these atoms, and so it's very radioactive. So this chemical process is all done remotely with robots and big shields, and it's very expensive. And in fact, it's extremely expensive, and it's never been commercially viable, and it may not be anytime soon. And then the other big problem is when you separate all the constituents, one of those constituents, of course, is plutonium, which someone could go in and steal, and they'd be that much closer to a nuclear weapon, which nobody wants. And so the traveling wave reactor eliminates the need for a reprocessing plant while still getting the benefits of a fast reactor. And how it does that is you just start your reactor with enriched uranium, like a regular reactor, but you put some low-grade depleted uranium or natural uranium out on the outside. And as it operates, neutrons go into that and get absorbed and become plutonium and start becoming higher-grade fuel. And you just slowly march that fuel, you move the fuel closer towards the center, and it slowly builds up more and more fuel from the low-grade stuff just by absorbing neutrons. And eventually it has enough fuel in it to actually come to power and take over the chain reaction from the enriched uranium. And so it's just breeding up, and then you burn it down without ever taking it out of the reactor to do any of this reprocessing. And so that gives you all, like I said, all the advantages of the fast reactor, but without the major economical and proliferation disadvantages of a reprocessing plant. And that's what TerraPower is all about. So, and my job there is, when I first showed up, they said, tell us where the neutrons are, what they're doing, and what they'll do in these certain situations. And so I started answering those questions for them, and then they said, how do you move the fuel? So I tried to help figure out how to move the fuel around, and I ended up building a lot of software that helps answer those kind of questions. So I sort of am half and half software development and core design and analysis. So that's what I do. And does that answer the question?
It does. If things go well, when do you have something that's going to be on the market?
Great question. So to be able to breed and burn the fuel like that, you have to irradiate the material more than anyone has ever irradiated a metal. There's structural metals in there. And so you have to prove that you can irradiate it that long. And a lot of the work TerraPower has done has been to develop metals that can handle that kind of thing. But you have to test it to prove to a regulator, that's going to work. And so what we've done is come up with sort of a stair-stepping development plan where you build a prototype using stuff we know will work. And the scheduled construction or the scheduled operation date for that is 2023 right now. We have been working hard on the design of that reactor, and it's at a pretty high level of design. We're looking for an industrial partner to form a joint venture to build it with basically known technology. And then using that prototype, we'll stair-step up to the doses required to actually to get this traveling wave capability.
Great.
So.
Tom Nugent is president and co-founder of LaserMotive, which is a really interesting story. Tom, tell us what you're doing.
Okay, thanks. So I'll admit, sort of like Nick, the younger version of me and the dream, which was back when I was in college, more than 20 years ago, which is sort of scary to say. I got really interested in all the work from the 70s, which was 20 years before that, of beaming power from orbit down to the ground. And this was going to solve all of our energy problems, because it was clear that population was growing, energy demand was growing, we need to get energy from somewhere. And so as a fresh-faced 19-year-old, it was obvious to me that we were going to have to build these solar power plants in space and beam all this power down to the ground. And
how's that working out?
Yeah. For those who aren't familiar with this concept, the idea is that the sun is always shining in space. You don't have clouds, you don't have night, and so you can put farms of solar panels in orbit, and you take this energy and you beam it down with like microwaves to the ground wherever you need it, and you have this power that's collected on the ground, and it's all nice and clean because it's solar power. But there's this little problem of getting everything up there and building, 20 square kilometers of solar panels in zero gravity. And so as I got a little bit older and started getting into this, I saw a lot of the economic problems as well as the physical problems involved in this sort of grand vision that people had back in the early 70s. But along the way, got to be interested in more generally resources available in space, which, as a side note, the Bellevue-based Planetary Resources is recently formed to go out and go after. And one of the problems I saw is involved in the cost of getting stuff into space. And so that led me in this sort of wide-ranging area to still be interested in transferring power, not by microwaves, which is sort of the way people looked at transferring energy from orbit down to ground before, but with lasers. The reason, obviously, of course, is because lasers are cooler. The other reason is that the size of your systems can be much smaller. So back in 2006, I met a co-founder, Dr. Jordan Kerr, who'd worked on power transfer with lasers for a couple of decades, starting back at Lawrence Livermore National Labs. And he had been following the trends in lasers and what are called diode lasers, using basically the same thing that's in an LED at a basic level, had been getting cheaper over time, following sort of their own Moore's law. They'd been getting more power at a lower cost and a higher efficiency. And back in 2006, he was like, you could start closing a business case to do power transfer with lasers for certain applications. And so we, at the same time, NASA started offering some technology prizes. They had one for a better astronaut glove, and you may have seen this, that there were half dozen or so teams that got involved, and this guy who had no experience in textiles or anything wound up winning this competition for making a better astronaut glove. Well, one of the competitions was in power beaming. And NASA said, here's the prize money. We want a third party to run the competition. The guys who said, yeah, we want this, were people who were doing space elevator work. And space elevator, you need to send power to this thing that's going to climb a cable up to space. So the competition was climb a cable and beam power from the ground. In 2009, we did that by sending power with laser to this little robot that got up to 1 kilometer in the sky. If people who aren't familiar with metric, that means about 3,300 feet up in the sky. And you're saying, okay, how'd you get that cable up there? There was this awesome guy based out in Olympia who's pulled cable for the Tacoma Narrows Bridge, who sat in his helicopter up at 4,500 feet with his little GPS system and held his position exactly rock solid for an hour at a time while we're sitting there shooting laser beams up at him. So that was an awesome experience out at the dry lake bed.
It doesn't sound like a really very good job.
Well, he was wearing goggles. He was safe.
Oh, okay.
Actually, it was amazing. At the ground, you could see this cable, and they had it split down, and you could see this cable that was sitting there at the ground. It would move like that. Literally, this is my hand. This is how much that cable was moving, with this guy up 4,500 feet above, keeping his position. So in any case, we won this competition by having this our cable climber go twice as fast as the minimum speed requirements. Speed was how they sort of measured how effectively you are transferring power. So at that point, we decided to commercialize the technology. And one of the first areas we looked at were unmanned aerial vehicles, what people more commonly call drones. Because at the time, there were a lot of these very small handheld, hand-launched airplanes that could fly for maybe an hour or two on battery power, and then they had to land, and you had to change the battery. Well, at the time, they were mostly being used by soldiers in Afghanistan and Iraq. And if you had to go out and change a battery, you were likely to get shot at. And the system, which at the time might cost $50,000 or $70,000, could land about 100 times before the hard landing destroyed the airframe, and you had to replace that $70,000. So we thought, hey, here is a great way to start power transfer. Here's a group that clearly needs to have the system fly for 12 hours instead of 2. And if you can be sitting there in your protected environment and not have to go out and change batteries, this has huge value. And so we did a series of demonstrations, taking a small helicopter and then a small airplane and flying it on laser power for ultimately many times how long the battery could have flown. And we sort of ran into all of the budget problems with Congress and the military sort of cutting back their R&D. And at the same time, we were starting to look at delivering power as well through fiber optic cable. And it's amazing how much power you can actually send through a fiber optic cable. People ask, oh, gee, can you, I know that you got your telecom, and that's maybe a couple of watts or something. How much laser power can you put through a fiber optic cable? The example I like to give is that there's a company based on the East Coast that is using off-the-shelf lasers with their own custom fiber and whatnot to send 20 kilowatts of power, 4 kilometers down to fiber optic to help drill for oil. They're cracking the rock to help save the drill heads. So 20 kilowatts is something like 25 or 30 horsepower of light going through a fiber that at its core is less than half a millimeter in diameter. So that gives you a sense of what you can send through fiber optic cable. So we've actually been getting a lot of success from groups who are interested in this, where they need to get power to somewhere where they can't have an electrical connection. So there are groups who are doing high voltage work, or they have our radio frequency sensitive devices where we need power. And so we're able to deliver that power that's electrically isolated. And what this means for us as a business is that we're taking baby steps. You know, we sort of, back for this NASA competition, demonstrated getting as much as a kilowatt of power out of a relatively compact receiver, and then getting power that went all the way up to a kilometer. And it turns out that for commercial interests that we're actually seeing, we don't yet need a kilowatt. You know, people are happy with 100 watts. Some people are happy with 5 watts. And the distances may not need to be a kilometer. In some cases, it only needs to be across a room or maybe a couple hundred feet. And so we are still working our way through to that really big commercial success, but we've had some pretty, for us, great small commercial successes in the last year for delivering power to customers that need it. And this, in my mind, sets a stage for delivering power at longer distances and higher power levels. Because people who talked about those dreams 40 years ago about delivering power from space said, oh, all you have to do is make a 5 gigawatt system in space and beam the power down. You're all done, right? That's easy. And our perspective has been, well, no, you have to run before you have to walk before you run, and you have to crawl before you walk. And it might be great to say, yeah, we're going to spend $100 billion to go and build a 5 gigawatt system in space. In reality, you have to show that you can do 100 watts. You have to start something small and work from there, because not only are people not going to believe that you can do the technology, but from a regulatory perspective, from a social acceptance perspective, people are not necessarily going to accept that you're going to send power through the air. They accept now that you can get data through the air, that you can get your cell phone and whatnot. But if I'm shipping kilowatts or megawatts of power through the air, people have to see that it's going to be safe. So we have been focused actually on the safety aspect of delivering power. The lasers exist. We buy those from vendors. The solar cells we customize from vendors. It's really tying it all together into a safe system so that I can say, yeah, there's a laser beam that's 10 feet away from my head that if I stuck my head into it and it was still on, I could be blinded. But the safety system around it is just like the safety system we have with electrical outlets in the wall, or the safety system we have in any other powerful device in our lives, that it's safe. It will shut itself off before you can hurt yourself with it. And so that starts down that path of showing, yeah, this technology will work, people will believe it's safe, and we're going to make commercial success at delivering that power to whoever needs it, whether it's a small flying vehicle, whether it's some industrial user that needs to get power somewhere that they don't want to run a wire because of problems with copper wires. And so that allows us then to start expanding to larger markets. Unfortunately, every year now for the last few years, there's been a major natural disaster where, first it was the earthquake in Haiti, then it was the Fukushima disaster in Japan, and now just very recently was the whole problem in the Philippines. Afterwards, the U.S. Navy is one of the aid groups that shows up to start helping those groups. And as sort of that next step for us, we're looking at disaster relief, where when these groups show up and they want to help, and in many cases, like in Haiti, the roads are all torn up, and you can't just drive a generator into this area. And even if you you could sort of get it in, then you have to try and transport in fuel regularly. You have these aid groups that show up, and if you're the Navy, you show up in a major naval vessel with tons of power on board that can see from practically a mile away the area it's trying to help. And power beaming would be a way to take that power that this rescue group has, send it in so that you can run emergency communications. You can power a field hospital. Maybe you could power pumps in a Fukushima. And that is sort of a next step to growing the power delivery that we see to eventually get to the point where who knows what people are going to want to do. Maybe someday the economics will actually say, yeah, you should beam power from space. I don't know. Maybe it'll never be true. But just like 20 years ago, people wouldn't have expected Twitter and everything with the internet, we really can't predict how people are going to be able to use power. But we know that by enabling new ways of doing it, by delivering it wirelessly over long distance, by delivering it in an electrically isolated way, people are going to come up with new ways to use it. And so we are building that for commercial success today to lead to even more interesting things tomorrow. So
what would you think would be the first significant market? Emergency relief, military? What would be your guess?
actually, right now, we are looking at this power over fiber has, for basically the same product, we're getting interest from commercial aircraft manufacturers, where in your airplanes, you want to isolate some of your flight critical sensors and actuators from your main power system. When your airplane gets struck by lightning, the aircraft is mainly safe, but you have residual current that flows around, and there are various reasons that it's actually getting worse now. And so if you can isolate those sensors, now your airplane can be safer. And similarly, one of the things we're looking at is in the electric power industry, there's this move to add more sensors into the electric transformers so that you can have the grid operate more efficiently. And so that you can run, this is something that Rob's going to talk about next, is to be able to have your transformers, which in some cases are 30 or 40 years old, be able to monitor them more closely so that you can run them all the way to the end of their life and know when the end of the life is coming and be able to do something with it before it blows up. So I think those kinds of applications where you need to get power into a high voltage or an RF isolated area are going to be the first commercial success for us. And there's some other things that I can't actually talk about that are going to be really cool that might wind up coming out into the consumer world, in the next few years.
So Rob Pratt is manager of the GridWise program for the U.S. Department of Energy at PNNL, the Pacific Northwest National Laboratory, which is one of our great research institutions here in the state. Rob?
Thank you, Tom. It's tough to follow these guys. National Lab, you think, okay, we're right on the edge. But Tom and Nick have talked about some things that are really out there and very exciting. So let me tell you, I'm going to answer Tom's questions in a little bit reverse order just to be obstinate. I think that's the rule for tonight.
Excellent.
So we'll start with the institution. Pacific Northwest Lab is 4,000 staff out in the desert in Richland. We do quite a variety of things. Basic sciences is one fundamental aspect of what's going on out there. We specialize in chemistry at the molecular level, both experimental and as well as simulation modeling we can actually do chemistry in computers now, basically, predict what molecules will do and how they'll interact. High performance computing is another example, advanced mathematics that we're heavily engaged in. Obviously important work. I won't go into why. I mean, it's not my field, but it's clearly advancing science in that domain. In terms of technology, we've got a lot of folks working in national security technologies, and those are critical for our nation's life and health in a sort of a dangerous world. And I can't tell you what those folks are doing because they can't tell me. It's sort of on a need-to-know basis. But three-letter agencies, as well as DOE and other folks. And then in energy technology, which is a directorate that I work in, we do quite a wide variety of things, from anything from fuel cells, basic materials and membranes, battery storage kinds of chemistries. We do a lot of energy work in buildings. We design the energy codes for the National Energy Department of Energy and the codes they promulgate through the states. and all kinds of building technologies, advanced lighting technologies, LEDs, and other such technologies, looking at improving the efficiency of our building environment. And then, as another example, is the power grid, and that's what I work in. And the power grid is anything from power plants, but it's mostly transmission systems and the grid, as we call it, the network, all the way down to substations in your neighborhood and the wires to your house and the meter on the wall of your house. So what's my place in this world? Well, I came to the lab 28 years ago. It's, my background is mechanical engineering, not power. I'm not a power engineer. I specialized in solar energy when I first started. So solar thermal was a hot thing when I was in grad school. Seemed like a good idea at the time. And when the tax credits went away, right as I started my career, so did my career kind of go away. And but it's a small putt from solar thermal in buildings to energy efficiency in buildings, and starting to try to make the buildings themselves work better and consume less energy. And so I had a consulting career. I did a lot of things backward in my life. So I had my consulting career first, and then I went to the National Laboratory. Getting to the National Lab, it seemed clear to me that modeling, at least, simulation, computing, even just calculating on a piece of paper the energy performance of building and building technologies was really simple and direct and not rocket science. It was a very interesting experience for me to come into the region here, which had just had the massive failure of attempting to build 5 nuclear power plants that they found out after they started weren't needed at the time. And the region got very interested in conservation and needed to understand what are people doing with these buildings that they're not consuming as much power as they were. And how can we accelerate that process? Very large end-use metering project for the Bonneville Power Administration back in the 80s was really the first big project I had at the laboratory. And we were metering 650 homes and commercial buildings at the end-use sort of device level, each circuit in the building, literally, and trying to understand what the heck is going on in buildings. And it turns out that, sure, you can model them based on all kinds of good engineering assumptions. That's the easy part. It's the people, damn it, that are the problem. And they do weird things like leave doors open or wash clothes in the middle of the night or fail to clean their furnace filters or waste energy in their buildings, or you have an identical building with identical demographic families right next to each other, and one consumes twice as much as the other for absolutely no reason that's apparent. So it quickly became clear that we did not understand as much about buildings as we thought, and in the process, that exposed me. This project was run by Bonneville Power, and they were interested in how the loads from buildings interacted with the power grid, you know, in a planning sense and a conservation sense, so that they could extend the wonderful hydro system that we have in the region to cover our power needs for more years. And that really got me involved in power grid issues and how power grids are planned and how they're operated to some extent. And that led me to my current career. So I like to say about P&L, 4,000 staff out there, we're the biggest bunch of nerds west of the Rockies and east of the west coast of the United States. 4,000 of us out there grinding away every day, inventing technology or trying to make the world a better place. So in 1999, some folks at P&L, myself included, a small group, came up with the notion of the internet revolution coming to electric power. And in 1999, the internet was well underway. It had personal computing and the internet had revolutionized business. It was revolutionizing entertainment. And why wouldn't it revolutionize the power grid? Gee, I wonder what that would look like. And you kind of rock back in your chair and stare at the sky and have discussions. We were very fortunate. This is not sponsored research. It was done on an initiative internal to the laboratory. And so we started a program called GridWise that year at P&L. And we chose that. We actually had an advertising firm help us choose that name. So it was very carefully chosen. So notice it's wise, not smart. So today the colloquial term is smart grid. And but some of the people that operate our power grid think that's a little insulting because they would say, well, the grid's already smart. You know, I'm smart. But the tools I work with are smart. They're not dumb. And yeah, and it's
Are
true.
they wise?
Pardon?
Are they wise?
No, they're not wise. They're not as wise as they could be. So, you know, and thank God for these folks. You hit the light switch, the light comes on damn near all the time. It's pretty amazing. It's pretty amazing. About the same time, to give credit where credit's due, some folks at Bonneville Power, a couple people came on the same notion, called it something different. A couple folks at EPRI, the Electric Power Research Institute, came on the same idea. And so these little skunk works started at 3 places in the United States. In fact, it even goes back even further. Folks at MIT in the 80s and 90s, I can't think of the professor's name, but there was a fellow that imagined a whole grid based on trading, which I'll talk about, trading of electricity and power in markets, long before that was even a rationally possible technology. There was no internet. There was no wireless communications. So our smart grid activity at the lab is really cut into a couple pieces. We work on what we call the bulk grid, the transmission system and all the generators. And the smart revolution that's coming there, I'm not going to spend time on tonight, but I'll tell you just quickly that it's all about new sensors that are giving us data with very high precision and very high frequency sampling waveforms, and you can understand what's going on in a power grid in ways that are beyond my skill set, frankly. Advanced visualization supported by wonderful computing and display technologies, and high performance computing, some of our national security stuff, technologies brought to the power grid, basically supercomputing to understand what those grids are doing in ways that we never could before. The bulk power grid is unstable, inherently unstable. The mathematical equations are unstable, which make them a pain to deal with, and the grid itself reflects that. It is unstable. Then we had a couple big blackouts in the Northwest in '96 that went all the way to California. We caused them. They suffered down there. 2003 blackout, the big one in the East Coast. When the horse got out of the barn in Ohio, it took 9 seconds to get to New York. And with our current data rates at 4-second intervals, that's 2 blips of data across 1,000 miles, and really the first indicator that the operators had that there was a blackout going on is when their lights went out. They didn't see it coming. They had no over-the-horizon view of that. So we work on that stuff a lot. Hurricane Sandy just occurred. What's interesting about Hurricane Sandy is it brought home the point that really big blackouts can be caused not by the bulk grid, but by your neighborhood power systems, in this case just getting blown down by a hurricane. Most blackouts are actually caused at the distribution level by cars knocking down poles. So the other part of smart grid, though, that I want to talk about tonight is what is really revolutionary, what is really a game changer, is engaging distributed assets. And let's start with loads, customer loads, the loads in your home, the loads in this building, other commercial buildings. And historically, the bulk power grid has chased the load around. The load is the master and the generators are the slave, and whatever the load's consuming, we have to generate almost literally instant by instant with perfection, or the unstable grid does collapse. Now there's a new paradigm with internet-type technology, communication technology to everybody's home and business. We can now engage the load as if it was a power plant. It's opposite, right? It goes down as like a generator going up. And do that by sharing value. I mean, you're not going to do that just out of the goodness of your heart, at least most of you probably won't. But if it is valuable to the grid and makes the grid cheaper, the point is to share that with you as an incentive and a reward to engage collaboration from you. The original concept was really centered around the economic efficiency of the grid. There's a whole lot of iron, steel, and concrete out there that's worth billions, hundreds of billions of dollars. And if we can avoid having to add to that, the point is that your utility bills will go down. Well, now we've got, since 1999, we've had this huge influx of renewable power in the grid. And it is a nightmare for these poor operators, because now not only are they chasing the load all over the map, but now they're chasing the renewable generation all over the map. So what they used to chase with is now starting to slip through their fingers. They don't have control over the renewable output the way they do a generator. So it's difficult, and they need flexibility at various timescales, and where they're looking for it, among other places, is from buildings. The other kinds of assets that we're talking about here are distributed generation, small generation. There's backup generators behind this building, I'll guarantee you, that nobody uses for anything ever except an emergency. Well, there you go. You can tap into that. Battery storage, distributed storage of various sorts, including batteries in electric vehicles at some point, can also be engaged, not just the loads. In 2006, we ran a project in the Olympic Peninsula that was cutting edge in showing how two-way communication could accomplish this engagement. We used the internet to send real-time price signals to 100 residential customers, some excuse me, commercial buildings. And lo and behold, despite how strange and exotic this sounded, we actually had success recruiting people. We told them, hey, you could save some real money, something like 10% on your annual utility bill. So, you know, pay attention to me for the next 30 seconds. You, the consumer, are in charge, not me, the utility. It's not Big Brother controlling your asset. You control your asset in order to earn that money as you choose. I'll give you automation so that you don't ever have to pay attention. You decide to do it. The machines take care of this for you. They gather the money. Fire and forget. Nobody's going to wait around for the next price coming in their house. I know I'm sure not. And adjust my lights or anything else. I need machines to do that. User-friendly interface. It's got to be real simple and intuitive. No mumbo jumbo. No techno speak. No loser proposition. Bottom line, that was absolutely critical, because people would say, how do I know I'm not going to lose money with this real-time price thing? And, you know, I can't even explain it. We tried explaining it to people in sort of like I'm explaining it to you, and whoosh, right over people's head. They really don't want to know. If they have to learn it, forget it. So we just said, look, no loser proposition. We will guarantee you will not lose anything against your standard bill. The worst that will happen is you pay your bill like usual. The best that happens is you get something back on top of that. We got 15% reduction in peak load from this community. We showed that we could get very short-term response with great precision and create a level playing field for these other kinds of assets as well. So with that, I'm going to stop. That's a little bit about me and what I do. We're almost like a company within a company when you're talking about 4,000 people. But that's what we're engaged in, and I'll tell you where that vision leads in the next part of this evening.
Hey, Rob. So the next question is that vision crystal ball one. I want to ask you personally what you think the future is going to be like. I'm not asking about your organizational or corporate position. Get out that crystal ball. What do you, as an expert in this very complex field, think may be the framework for a new future energy paradigm? Changing energy systems takes a long time. How long does your paradigm take? Nick?
Well, of course, my personal preferences are perfectly in line with my company, right? Is this thing on?
You're violating the rules already. One sentence in.
Damn you! Sorry. We have to be oppositional, right?
Oh, right.
Well done.
Beautiful. So, okay, the paradigm that I see in the future is basically, it's simple. Fossil fuels are bad, and we have to make a huge amount of energy and somehow reduce the amount of fossil fuels. That's basically what I start from. And then to understand how big of a deal that is, I have to go back to the graphs you were tossing about. Are they still down? About how big the energy problem actually is. And so I like to try to conceptualize how much energy we actually use. And if you look at the numbers, you'll see something in the quadrillions of BTUs, and you won't know what that means because nobody can visualize a quadrillion, much less a BTU.
That's really not funny. You're a bunch of energy geeks.
So I have this little visualization that I like to go through. So take a city of 700,000 people. That's a little bit more than Seattle. And that many households can be powered electrically by a 1 gigawatt power plant. And that's typical for a large nuclear power plant or a big coal plant or whatever. So say you wanted to replace that power plant with a solar plant. You'd have to make it about twice that big, and you'd save the extra energy for the night once the sun goes down. And the easiest way to consider or to visualize stored energy is to think of the concept of pumped storage, which is what hydroelectric dams sometimes do, and they pump water back up into the reservoir when the electricity is cheap and then let it run when electricity is expensive. You can do the same thing to store energy. You just lift something heavy up something tall, and you can kind of visualize that, I thought. So let's go through it. So how tall are you going to build something? I figured, okay, let's make an easy assumption and say the Burj Khalifa, which is 818 meters, tallest building in Dubai. And if you've been to Dubai, you'll know that that's actually quite a large structure, and it's probably not that capable of holding large weight, but let's assume it is. And so the question becomes how much stuff do you have to lift up there to power a 1 gigawatt city through the night, 9-hour night. And I thought maybe we'll do pickup trucks to start, but it was a fairly large number, 2.2 million. So I needed something bigger, and so I decided something big would be a fully loaded Nimitz-class aircraft carrier, fairly large object that you may have seen around. And so you need to drop 44 fully loaded Nimitz-class aircraft carriers at 100,000 tons from the top of the Burj Khalifa, every night in order to store that kind of energy. And so that's just kind of the visualization of one
So
power
for one city of 700,000, that'll provide nighttime energy.
Right, for 9 hours.
Only 44 aircraft carriers.
Right, only 44,
Yeah.
yeah. And then, during the day, you have to have twice the solar capacity of the city to lift them back up, or whatever you're trying to store. It can be any kind of energy. It doesn't have to be solar. So that's just one way to visualize it. And now, there's a huge amount of energy in the fuels we use, and it's much denser than aircraft carriers. So, for instance, if you did this with lithium-ion batteries, you'd fill a football field, and it'd be about 6 meters tall of pure lithium-ion batteries. That's going to run you about $4 billion, and that's assuming perfect charging efficiency. So that's 18 feet, by the way. Point something. Anyway, okay, so that's one city. What's that?
But a flow battery that's more realistic.
Sure, and the advances in batteries might be, I'm not sure what the energy capacity is, but it may be smaller. The current,
And cheaper.
yeah, absolutely.
I mean, it'd be better to use as your visualization actual reasonable ideas instead of bad ideas.
The purpose is to
First of all,
instill
there's a rule
knowledge
here.
of how big
You're
the
not allowed to
energy
be
is.
funnier than me.
Did you plant him, Tom?
No.
It's a fair point, but the idea is to sort of, people can't visualize how much energy we use, and the idea is to show you something big moving, and it's really hard to visualize energy capacity. So I'm showing mechanical things that you can almost visualize. It's definitely a bad idea, but the point is to visualize the scale, okay? And so I'm going to actually keep going with this analogy. And so there are 440 gigawatts electric being used in the United States on average, so you now are up to 20,000 aircraft carriers dropping from the sky every night. Electricity is, of course, only 40% of the United States' energy use. The rest is transportation, fuel, and heating. So if you electrify all that and put in pump storage, you're now up to 50,000. That's 1,000 per state. And if you lined them up along I-90 from here to Boston, 3,100 miles, and you went 70 miles an hour, that's one every 3 seconds you would pass by. So, and it would, or a large battery bank. So the point is that there's an incredible amount of energy that we're using, and it's a big mistake to think that, oh, my little idea will be able to fix everything, because the scale is enormous and it's growing. So when I look at my crystal ball, the United States currently uses 20% of the world's energy. By 2040, that the world's energy will have increased 56%. That's an unbelievable rate, and almost all of it is in non-OECD countries. And that's the prediction, but the reality is that in 2000, China used about half the energy that the United States used, 2000. And today, they use more energy than we use, and we use 20% of the world's energy. So you can kind of understand that that growth rate is completely astounding. And they're building a coal plant a week. Each coal plant takes a 1 mile long train of coal per day. Okay. And
Well, if you drop the coal off an aircraft carrier,
you're not the first to bring that up. Hilarious. So the point is that we need a huge amount of, well, I haven't made the point that fossil fuel is bad, but I can do that too. We need a huge amount of low carbon energy from somewhere, and it's growing. So right now, to displace the amount of fossil fuel, which, by the way, that 2040 prediction, I'm not looking in a crystal ball, I'm looking at the 2013 Energy Information Administration International Energy Outlook published last July, and they say the vast majority of that increase will be coal and gas. And why? Because it's cheap. And when you're in a non-OECD country and you're building that fast, the only thing you care about is cost. And so now, one point against fossil fuels, in case anybody needs any reason not to like them, an interesting study last March published by James Hansen, the guy who basically invented climate change in the 70s, did a life cycle analysis of nuclear reactors and found that if you consider worst case scenarios for Chernobyl, 3 Mile Island, Fukushima, nuclear energy through its lifetime has saved 1.8 million lives. How did it save them? By displacing air pollution-related deaths associated with fossil fuels. So you saw the news in China a month ago where the whole city of Harbin or whatever, was shut down, 11 million people, incredible particulates in there. And so even if you forget about global warming, the air pollution-related deaths associated with fossil fuels, in particular coal, are astounding. And so nuclear displaced enough, it's 6% of the world's energy, it displaced enough to save 1.8 million people total, again, assuming worst case for all the accidents. And that would have been the same had it been renewables or any other low carbon energy source that would have displaced the same amount had they produced that much, which of course they didn't. Basically, this whole argument is kind of turning into the fact that presumably you agree that we need low carbon energy. Presumably you agree with the EIA that there's a huge increase in energy demand, and presumably you agree that it's going to be in the third world. And so when I look at what we're going to do for energy, I see the need for incredible amounts of cheap, low carbon energy. And when I look at that, I see advanced nuclear energy, like the stuff that TerraPower is doing. There's also another pretty interesting concept that I kind of like, which is, it's kind of a crazy idea, so I'm sure I'll get a comment. Say you had like an energy emergency. You realize global warming is going crazy, and you need to build tons of carbon-free energy very quickly. You could consider going into a shipping port in South Korea or a shipyard and start building super tankers with large nuclear reactors on them. Reactors have been on ships before, you may know. In fact, in Haiti, the thing that was providing all the energy was a nuclear-powered aircraft carrier, and it was providing fresh water and electricity. You can put even bigger, you can put large 700,000 people serving power plants on these huge super tankers. You can build them extremely quickly in those shipyards. It's modular construction. The construction guys are always working. You pump them out as fast as you can. They deliver themselves to wherever they need to go and do some reasonably long transmission lines. They park 10 miles offshore, so if there's an accident, there's 0 people in the exclusion zone. They are intimately coupled to a very huge heat sink, the ocean, so it's not difficult to keep the reactor cool even in a crazy emergency. There are no earthquakes. There are no tsunamis, because tsunamis only happen on the shore. What else? Oh, and for weapons proliferation, if they need to refuel, they can drive back to their weapons state home base, refuel there, and go back, so the person that they're serving doesn't need to have fuel cycle infrastructure. And the Russians are actually building power plants on ships right now, fairly small ones. But this is the kind of idea that I think when I see, if we need to start building energy and it has to be low carbon, then that's the kind of thing that I turn to myself. And I'm hoping for more questions in the Q&A.
So thanks, Nick. So you see a future with like 100 billion aircraft carriers falling off buildings. Tom, what do you see?
So getting all sorts of interesting ideas from both Nick and Rob. And so you're going to have to cut me off at 10 minutes because I think I'm going to blather on for a good long time.
All right, I can do that.
First thing I'm going to take issue is with one of your charts where you showed the decreasing energy per capita, or decreasing energy per GDP of the US. And I think Nick sort of made this thing, which is that, in a sense, we're outsourcing a lot of our early stage high energy production stuff to China. So it would be interesting to look at that number and say, okay, how much of what counts as our GDP is, say, an iPhone that's mostly manufactured in China, where you have a lot more energy production. So it's that thought of whether or not.
I'm sorry, the chart says the opposite.
Oh, okay. So it'd be interesting to look at that from a global perspective. So before I get to my own vision of the future, the other thing about something Rob mentioned about, sort of telling people you can save money, suddenly struck a thought in my mind about high frequency trading on Wall Street. And the stories where these people are spending gobs of money to get millisecond advantages over other people and information. It leads me to wonder if the infrastructure allowed for it, if you'd start having neighborhoods and people trading, how much am I going to turn down my air conditioner or my wash machine to get the energy savings from the power company before those guys, half a mile down the road are going to try and do the same thing. So I'm wondering if there is a future of basically high frequency trading for energy modulation to meet the baseline power.
Short answer is yes.
Okay, cool. So, settling into sort of my thoughts about the future, which are also going to be similarly wide-ranging. My thoughts about the future are focused sort of on what I know in terms of power delivery. In a sense, what Laser Motive is doing is extending the electric power grid. Into high voltage areas, yeah, that's one thing. But when we're flying aircraft, it means we're taking this power grid, which is under the ground and in these power lines a few feet above the ground, and extending it really into the sky. And so now you can imagine a future. This is just one of many futures you can imagine where drones see a lot of civilian use. And you have aircraft that are serving lots of functions that used to be fulfilled by people. You may have seen some of these sort of half-joking suggestions about the taco copter, where you're going to have your taco delivered by this little tiny helicopter. And I'm going to argue that 10 years from now, that's not going to be a joke. That in fact, a lot of small package delivery may in fact happen by flying robot, because people are expensive. Running a fleet of UPS trucks and FedEx trucks and US postal trucks can be very expensive, as well as paying the people to run them. Whereas if you have little robots that can carry, a letter, a FedEx package, a pizza, whatever, and you don't have to pay a person to do it, then that becomes a very interesting economic argument. And now you have all these little tiny robots flying all over a city, and you still have to pay a person to change their battery. Well, if you have power delivery that's been extended from the ground up into the air, now you can have these things get their power wirelessly from transmitters that are on top of a whole bunch of buildings, in the same manner that you have cell repeaters on tops of various buildings. And now you've taken this power distribution grid and extended it into the sky. You now have this capability of delivering packages from, same day delivery from Amazon or whatever. Your Amazon warehouse could have a little airplane or something that's going to take your box from the shelf at the same day, fly it out to your house, and that airplane is get powered along the way by lasers from on top of buildings, so that when it gets back, it doesn't have to worry about recharging its battery. Its battery has been kept topped up all the way along its path. So that's just sort of one vision that I see is not at all crazy when you look out 10, maybe 15 years. Once the FAA sort of says, yeah, you can fly these robots, people are going to be using them in all sorts of ways. Again, ways that you can't predict. 10 years ago, if you said, yeah, you're going to have tacos delivered by helicopter, you would have laughed. But you know what? Domino's in the UK has a video of someone delivering a pizza from a copter. This guy comes down, and you can see on the video, he takes the pizza out of the copter and takes it into his house. So there are things like that that I think are just going to astound us. You can imagine all sorts of different ways that people are going to use energy. One thing, and I'm going to admit to my very faulty memory here, I don't remember the name of the effect, but the effect is that as energy use becomes more efficient, we actually wind up using more energy. I forget the name of that effect. But there was a very interesting article in, I think, the Wall Street Journal just this last week with an interesting chart comparing energy generation and energy consumption from 1993 and 2011 or 2013. And you look at which nation generated the most gas, which nation had the most coal, and how that worked out, and which nation consumed the most power. And if you look at the US, power consumption from 1993 to 2011, it barely budged. Maybe it was a 5% increase, maybe a 10% increase. It was, like you guys have mentioned, all the developing nations that have quintupled their energy consumption over the same range. Well, the US is getting more efficient at certain things, like your washing machine and your refrigerator are more efficient. Your car has gotten more efficient, but you've also started driving more miles. So that's sort of been a wash. Well, now as other things start getting cheaper, are you going to start having all these robots come out that are going to take up the slack, as it were, and start using energy in new ways that you might not have thought of before, that are going to not allow your total energy consumption to go down? You're just going to keep using energy, maybe even a little bit more, to do more and more things. So no matter what people do with conservation, which is great, we're still, as a society, probably going to keep using as much power as we are now, maybe even more. My thoughts on the future, with what Nick's talking about for storage as well as for generation, there's a lot of interesting ideas out there for how do you deal with the variable nature of wind and solar and all these renewables. And there's people talking about large-scale energy storage, like I mentioned before, Don Sadoway from MIT has this liquid battery where it's basically a giant aluminum smelter that you sort of run in reverse and operate as a giant battery. And that can use low-cost metals and can store sort of grid-scale power overnight. Well, now it's a question of, instead of having your generation chase the load and your operators chasing the generation and the load, now you get what's in a sense a capacitor in the system that can buffer that. And that may have unforeseen effects of not only being able to store that energy, but then it's a question of transmission and transmission efficiency. And this is one question that we get when people are asking us about, well, how efficient is your laser transmission? Well, okay, peak efficiency today is about 25% end-to-end. And depending on your perspective, that's either really great or really horrible. If you're talking grid scale transmission, 25% efficiency is horrible. You're losing 3/4 of your power. If I'm trying to take something that needs a couple hundred watts and I need 4 or 5 times that energy, well, that's still one plug in one outlet out there can still generate, a lot more power than that. And at 10 cents a kilowatt hour, I don't care. If I need 100 watts in the sky, it's worth that extra 10 cents of electricity here on the ground in order to do it. And so when people start talking about comparing different ways of generating, transmitting, and storing energy, this whole efficiency question becomes very, very complicated. So there was an example before. If you're charging a battery, for example, that's not perfectly efficient. You're going to lose maybe 10%, maybe 15%, depending on what it is, maybe 5% to charge that battery, or to pump that water back up into the reservoir. Okay, well that's one efficiency, but now you have to transmit it. If I have to transmit the power 1 mile, I have a certain loss in my overhead voltage lines. If I have to transmit that power 500 miles, well, I don't think I'm actually doing that in one shot on a high voltage line. I'm more sort of shifting my power 50 miles down the road, and they're shifting their power 50 miles down the road till it gets to where it wants to be. And so when you start looking at that as a whole picture, you have to start asking, okay, if electricity is really expensive here right now and it's cheap somewhere else, at what point do I not care about the efficiency loss? Where, for example, would 25% efficiency still make sense because energy right now in this moment is 20 times as expensive as it is over there. And I don't care if I lose 3/4 of that energy, I'm still saving money by transmitting that power 500 miles over here. So there's going to be a lot, I think, of development in the next decade or two of getting sort of models that become sort of the equivalent of the high-frequency trading computer systems that are going to look at juggling all of those factors of efficiency, generation, storage, transmission to figure out what really is the best, which means, in a sense, cheapest way to get energy to where it's needed. So that's my rambling. I don't know if that's 10 minutes or not, but those are sort of my thoughts on where the future is going.
Thank you. So, Rob, Nick sees a world with aircraft carriers falling off buildings.
Yep.
Tom sees a world with skies full of pizza-delivering helicopters. Can you please save the evening?
That's a tall order. The path that we're on in this country is towards renewables. I mean, the answer to the questions, not necessarily globally, the ones that Nick was raising about where is this energy going to come from, in a zero load growth society, which is roughly what we are now. We've roughly reached equilibrium. Then there is the opportunity to catch up with renewables as they get cheaper. When I was in grad school, they said natural gas is going to run out in 5 years, and it didn't. And 20 years later, they said it was going to run out in 10 years, and it didn't. And now we just fracked our way into a natural gas future. That'll be an interim strategy. But at the end of the day, at least in this country, people are talking about 80% renewables. And I was a big fan of renewables as a young man. I still am. But the bottom line is they've got to be affordable, or we can't get from here to there. And there's an unfortunate implication of renewables in that you're tied to the sun and the wind, and it does get dark and the wind doesn't blow all the time. And so from a power grid operator perspective, you got to have something to fill in the gaps, barring some super batteries or some aircraft carriers on buildings. Or barring nuclear power to fill in those gaps. And so it starts to beg the question at some point, the cost on a per unit basis of renewable power as you start to approach 100% renewable goes up and up and up and up because you're having to dump it because you can't use it all the time. You have to have way more than you need because we can't store it. And either you've got to ship it from the bright side of the world to the dark side, or you got to ship it from where the wind's blowing to where it's not blowing, or you got to have batteries or something else. And so life gets very complicated. Before I dive into what I really wanted to talk about, I think I'm going to step back and do the long crystal ball gaze a little bit. I may have to follow these two guys, a little bit of that. To me, the one issue that really seems intractable. Let's say that we in this country go renewable electricity. A lot of end uses that are currently powered by natural gas will convert to electricity under that scenario because it's clean, right? It's carbon free. And so eventually, if that's an imperative, that's the way the world starts to push. The one place that doesn't really work very well is vehicles. Whether they're flying pizzas around or driving down the highway, either one. And so we basically have a couple choices there. And looking at what my kids and grandkids are going to face is either we're going to have electric vehicles and we'll be pumping a lot of that renewable power on those vehicles, preferably in the daytime when it's plentiful or when the wind's blowing and it's plentiful. It certainly helps the power grid sort of fill in the valley when we all go to sleep at night and aren't using as much. There's something for the power grid to do to make some money and keep costs low on a per unit basis. So that's one possibility, but the whole deal there is the cost of those batteries and range anxiety. Maybe we solve those problems satisfactorily, maybe we don't. I have some faith the automobile fascination that this nation had when I was a boy and I was part of it is largely going away. I mean, my kids didn't rush down to get their licenses. I couldn't believe it. What's wrong with these people? And a car is not quite the same status symbol that it was. And so there's some hope there, but at the end of the day, you start to think about things like power beaming, as another way to solve that problem. I don't think it's going to be hydrogen on those cars. It's too inefficient. So which brings me to my major point, I guess, that maybe the clearest part, or the part of the crystal ball that I'm gazing in that seems the clearest to me, is that however you get your energy, you've got to be efficient at utilizing it. Delivering it and utilizing it is sort of fundamental. Now, there are niche applications, and Tom's absolutely correct, and delivering a pizza might be one. Cell phone is a great example. The cost of the electricity on that cell phone to make that cell phone call is nothing compared to the value of that call based on the size of my cell phone bill to the size of my electric bill, right? I mean, the electricity there just doesn't matter because it's convenience that matters, and there will be niches where convenience matters, and whether that power comes out of an expensive battery or comes out of a beam in the sky or something else doesn't matter. But the bulk, the large just chunks of energy that we use as a society for heating and lighting and running computers is always going to be a valuable commodity, and it's getting more valuable. As we switch to renewables, the prices will go up. If we bring in other new sources, prices are going to go up. It's never going to be too cheap to meter. And so we've got to be very, very careful with how we manage it, that infrastructure that delivers it, and especially how we utilize it. So what we envision is an Internet of Things. You've heard about that from people that are not in energy probably. But in fact, this smart grid stuff is really the first tangible reason why you might want an Internet of Things. And if we are going to engage millions of devices or billions of devices in millions of homes and businesses to engage a marginal amount of flexibility on each of their part, to help us manage the power flow through our wires, then we need a system to control and coordinate those, because otherwise they're as bad as the renewables. They're jumping all over the place. I mean, we need a control system for this stuff. And the trick is, the power grid doesn't own any of it. Y'all own it. We all own it. It's not the power grids to control, and none of us are inclined to surrender it to them to control. So how do we put this together? So the first part of that vision is how can we gain these infrastructure utilization advantages, and that is this Internet of Things. Fundamentally, it's kind of, we have a notion we call transactive control and coordination. It's a bunch of micro transactions that engage these devices. Each device sort of expresses its flexibility in terms of, here's the price at which I'm going to switch from on to off. So everybody's got a price. We're just negotiating the price, right, to paraphrase the old joke. So then at the building level, you add these up, and now you have a sort of a stair step, a bunch of devices, and you remove all the tags from those devices because it's none of the utilities' damn business what those stair steps represent, whether it's your car or your TV or anything else. And then you deliver that to the utility, who adds them up for everybody, and now they've got a demand curve, a price versus demand curve, and they can set a price to get exactly the load that they need at any point in the power grid at any point in time. Now, it's very important to understand that that is not a free market. They can't just set those prices any way they want just for the purposes of control. So there's a whole financial engineering side of this that makes this revenue neutral, so that customers are not getting hurt by this, that it's essentially a zero-sum game. And if the customers respond, they get a financial advantage. So the utility can set that price, send that price back to the device, and as long as those devices are being honest, literally expressing their intentions with price, when that price gets back there, that device will do its on-off thing or stay where it is, just like it said, at least for a short period of time. And that is the process. That closed loop is the key to getting control out of a network of devices that you do not own and literally control. So it's an economic transaction-based control system, if you will, but it's actually coordinating, not controlling. So that is great for the grid. And just to give you a sense of scale, it's not a panacea. It doesn't solve the world's energy problem, and it doesn't even say we're never going to build any more infrastructure for electricity in the United States. What it does do is say that, for example, if everybody in Dallas, Texas would give me 2.5 degrees Fahrenheit on their thermostat in exchange for a fee, on the hottest summer day of the year, 100 degrees Fahrenheit, humid as hell, we get 12% reduction in the peak load from that population. That's billions and billions of dollars of infrastructure that we don't need to have sitting there just for 20 hours a year when it's that hot out, or 200 hours a year when it's close to that hot out. So that's part of what we see happening. But I want to take it one step further. By the way, we are doing a couple of demonstrations of that technology. One here in the Northwest, the Pacific Northwest Smart Grid demo, and one in Ohio with AEP. But there's now folks that have taken this a step further, and I wish I could take credit for it. I'm a participant, but I can't take credit for it. So God bless them. They're extending this vision of a transactive power grid control to something that may be called transactive energy writ large. And that is, again, leveraging this IT system to do other things. So once you've got this information and communication technology in place, all the way down to the roots of the power grid, now you can begin to leverage that system for advice. Like, dump that fridge, buddy. You could buy a new fridge and it pay for itself in 3 years. Or diagnostics on commercial buildings like this, which frankly waste energy like crazy. Is everybody comfortable in their offices at work? I mean, you're always complaining, hot or cold, cold summer, hot summer day, your office is cold, vice versa in the winter. That's wasted energy, and there is a lot of it in the commercial sector. People say as much as 25%. Advice on energy efficiency retrofits, like, gee, you really need to be, you're losing a lot of heat out of this building in winter, and oh, by the way, here's a utility program you can go connect to. Here's the internet link, click on here. There's financing, there's contractors, et cetera. But it goes even further than these kinds of things. That can save a lot of energy, make the system more efficient. You begin to start trading energy services, and you create a new sort of vibrant economy with the innovation that private enterprise sometimes only seems to bring. So you could have third parties that come in and put a battery on a building and sell you the electricity from that battery when it's to your advantage. So they're doing the financing, and so you now have two sources of electricity, the power grid and that battery, and maybe the PV cells on the roof as well. And even using these paradigms to control the heating and cooling systems in buildings, thinking of a market transaction paradigm of transferring energy into its chilled water form, into the air-conditioned form that then this zone of this particular building is buying from the HVAC system, and using that economic paradigm as the optimization routine, if you will. Economic markets have a property of being somewhat self-organizing and self-optimizing, and so you could kind of achieve plug-and-play kind of control and self-optimizing control using these paradigms, we think. Some people think. It goes even further. Think about just convenience services. So there's people that are actually thinking of this, apparently. Down in San Francisco, the BART metro system has EV charging stations in the parking lots, and there's only a couple of them, and there's getting to be some electric cars down there, and so you have to pull a tab and they give you a position in a charging queue. And if you're planning on getting back to your car and having it fully charged and you're going to be back in a couple hours, you might just be out of luck because there's 12 other people ahead of you and it takes an hour each or a half hour each or whatever. Well, somebody's going to build this app for mobile phones that allows you to trade with other people in the queue, basically buy their position out. So you get there early, and now you got a position, and then you can sell that position and make a little money. So pure convenience type things. overall, and it's building on something that Tom was saying, is that I envision this information technology as allowing us to optimize the overall system from source, meaning generation of whatever sort, to the sink where it's used. And the trick with that optimization today is that it always is within an enterprise, like your home, or this building, or the power grid, or the power plant. And nobody's looking at the whole system. And by connecting it together with a set of economic transactions, all of a sudden you can unleash value that crosses enterprise boundaries. And you're allowing people that can help by doing something here where the benefit shows up somewhere else, you allow them to basically share that and trade that. And then that makes good things happen. So I envision a world in which I know you just said no one could visualize a BTU. I'm not sure I've ever seen one run by either, and certainly not in a Halloween costume. But I envision a world in which, just like you say, no stone goes unturned. I think this will be a world in which no kWh, unit of electricity, power, or energy, and no BTU on the thermal side goes unexamined, both within your enterprise and then looking at the system, the whole supply chain. And if it's not in your domain to optimize, you make a trade with somebody else that can. So that's our vision for the world. That's my vision for the world.
Thank you. I believe we have 15 minutes for Q&A and audience participation. Is that correct? Sir.
You all spoke in what I believe to be domestic terms about what you're doing. So where are we relative to the rest of the world in the areas that you've addressed?
That's me.
Could you ask a question into the mic, please, so we can
I'm not sure I can ask the same question.
Ask a different one.
So you spoke in mostly domestic energy terms tonight. Where are we relative to the rest of the world in the fields that you now occupy? Are we leading, trailing, or somewhere in the middle?
Go in order. Okay, so in advanced nuclear, we used to be leading. We basically, the United States, the National Lab System, and obviously the United States invented nuclear energy and went on to develop reactors and then advanced reactors. But since then, we've sort of fallen behind, and we've shut down all of our advanced reactors. We had one at Hanford, and we had one in Idaho. And so the rest of the world has sort of said, or other people in the rest of the world have said, oh, we are actually interested in these things. And so there are several operating advanced sodium-cooled and other types of reactors. There's some in Russia. They have probably the most experience. France has had some that they're now shut down as well. And India just built one, and China just went critical a couple years ago with their advanced reactor. So the only advanced reactor game in the United States right now is basically TerraPower. We have about 70 people over there working on it, whereas in places like China, there's like 500 people working on each of their different advanced nuclear concepts. So we are definitely falling behind in the field that I spoke of.
So there's a couple different parts to this. Just as a side note, I lived in Japan for a year, and when I was there, this was back in 90-something-5. There was, I remember on the news in Japan, some liquid sodium reactor leak problem that was a big deal back then.
I forgot to mention Japan also had some reactors.
And in for the last 15 years, Japan is sort of they've had sort of these ideas about, hey, we're going to do the solar power and beam it down from space, and it's like, yeah, it's a nice idea, but nothing's really happened from it. And I've just heard very recently, because of Fukushima and the sort of strong push to maybe get away from nuclear, and while they don't have many other options, there might actually be a push there for getting more serious about work in power from space. And there's been, if you're in the sort of power from space community, a few of the big people who do work in that are in Japan. So it's not clear, in power beaming, I think U.S. is still in the lead. Hell, as far as when customers come and find us, they say Lasermotive is the world leader, so I think the U.S. is the leader in that right now. But looking at broader, power beam, there's still a lot going on in Japan. Looking a little more broadly, if you follow the story of solar power in the last decade, there's been all of the story out of China with their, and you could say it's sort of misallocated capital, but there's been this capital that has created production capability that has caused the price of solar to sort of fall through the floor for a while. And there's some interesting charts that if you look at the dollar per watt of installed solar and how it's sort of falling very steadily over time, and you project that out, and sometime around, I think, 2020, it gets cheaper than, I can't remember, coal or oil or gas, some of the more common power systems. And at that point, you say, okay, you're not necessarily going to need all the incentives to build solar. Suddenly, solar will be, minus the problems of storage and distribution, the cheapest way to install new power capability. And so it'll be interesting to see if China maintains their sort of lead in production capability, as that price keeps falling, if that winds up being a continual advantage, happening out of China.
Anything to add, Rob?
In the smart grid area, we invented it and then we promptly gave it away. I'd say we're still on the cutting edge, but the Europeans caught on very fast. And they're making great strides especially in terms of the integration of renewables problem, because they took it upon themselves to get a lot more renewables in their power grid faster than we have even in the western coast here. And so they have really made advances in that. In terms of engaging customers and their loads, however, I would say the U.S. is still the leader in that. In Europe, they don't have the peak load problem, and so they didn't get an early start on those kinds of approaches. They're much more interested in batteries and other kinds of technologies. And so I think we have a niche there, a strong niche in energy efficiency, a strong niche in how to engage buildings in offering their flexibility. I and some other people think that'll be an exportable technology that the U.S. can hang on to at least for a while, and it'll be important in other parts of the world that are hot, especially as their GDPs pick up and people can afford air conditioning and a better, other kinds of discretionary uses of energy. Then these kinds of technologies would be a lot more important.
Other questions, sir?
So this is directed to Tom. You were saying that you had about a 25% efficiency. What's your best case, worst case scenario for efficiency, say 5-10 years down the road?
So there's been a lot of work in making solar cells more efficient. You keep seeing these areas where, okay, what you buy off the shelf might be 15 or maybe 20% efficient, but in the lab, they get up to like 40-some% efficiency. And there's been a lot of motivation in the research area to increase that efficiency. And the problem there is they have the entire solar spectrum to work with. For what we do with laser power beaming, we can choose one color of laser light and match that to the peak efficiency of the solar cell. And so we can get out of the receiver part of things 50% or so efficiency. You do some tricks, maybe you can push up to 55, maybe 60%. But if you look at, okay, what's a theoretical maximum efficiency for monochromatic conversion in something like a photovoltaic, and depending on who you talk to, it's 85% or more. And so it becomes a question of, is there motivation to do research to improve that? So if you look at things that are foreseeable with both the transmission and the receiving side of it, we can see getting above 30% in the next 5 or so years. And looking out to 10 years and beyond, if there were a push, you could maybe start getting into the 40 to maybe 50% end to end. But that's going to take a lot of work. So it's certainly within the realm of possibility.
A question over here.
Yes, so I had we've heard a lot of talk here. The question that I had is around waste. So it's sort of two parts to that. One is the nuclear question of waste. If we have the waste of fossil fuels that we're breathing in pollution and all that sort of thing that we're trying to eliminate, nuclear still has a problem with what do you do with the spent fuel. And then the other part of it is pricing in waste. Rob, you talked about the market solution. Are we going to see a market solution around building the cost of waste disposal into the upfront price that everybody's dealing with and see any kind of solution there?
Nuclear waste. Surprising question. Kidding. That's a great question, and the answer is for nuclear waste, the technical ability of humans to safely store nuclear waste is a solved problem. We have an operating waste repository in Carlsbad, Nevada, where they store weapons waste in the salt deposits. It's surprisingly successful and is considered to be perfect for commercial waste just as well. There's a new technology, thanks to the drilling companies, ironically, called deep borehole disposal that I just watched a presentation from Sandia National Lab just last week where they said they can drill holes 5 kilometers deep into this reducing environment, into the bedrock, crystalline bedrock. You can put 400 assemblies down there, waste assemblies, and then you backfill it with a bunch of concrete. They cost $44 million each to drill, and that cost comes out to be half what nuclear power plants are already paying into the nuclear waste fund to take care of their waste. So something people may not know is nuclear reactors have already paid for their waste disposal, and the government just has to figure out what it's going to do with the waste. So there are plenty of technical options. Yucca Mountain was another one, and maybe wasn't as good as these deep boreholes. So the waste problem is definitely a political problem. It's not an economic problem, and it's not a technical problem.
So let me ask you this. Years ago, I used to work at Intellectual Ventures, so I was there in some of the early discussions about TerraPower, and I remember them talking about that the traveling wave reactor was effectively burning nuclear waste. That they would take what's today nuclear waste and use it as fuel, and that you didn't mention that. So is that not the case?
That can be the case. The main line is that it burns not highly radioactive waste, but rather the waste from the enrichment plant, so the tailings out of the enrichment plant, which is not very dangerous. However, the advanced fast reactors, I mentioned reprocessing plants. If you use fast reactors with reprocessing plants, you can treat your waste so that it decays to the level that it was when you dug it out of the ground after only 300 years, and you can actually burn the rest of it in this fast reactor. Versus other waste, which lasts 100,000 years. So, and our reactor could do that, but it would need a reprocessing plant to do it, which we've kind of said we don't want to do for the economic and proliferation reasons. One other point with nuclear, there's so much energy density that in a traditional reactor, if you got all of your electricity as an average American for a year, you would produce 40 grams of nuclear waste. That's as much as 7 quarters. It'd be very dangerous, but it's extraordinarily small compared to the amount of waste you generate from the chemical fuels.
You just need to send it to the center of the earth.
So the deep boreholes.
A point I wanted to make about that relates to the nuclear power question in sort of an interesting way is that there are issues surrounding the capture of carbon dioxide from traditional coal power plants and sequestering that in the ground. And the problems are associated with the liability of what happens if that were to somehow escape and leak out, because carbon dioxide is heavy and kind of would linger on the ground and basically kill people. And so in the same sense that the waste is a stumbling block for nuclear power that's been tough to overcome, they're not the only technology that suffers from those kinds of issues. And so you always need to think about the waste streams. And so in terms of the trading systems that I've been talking about, absolutely we think about incorporating what are commonly called externalities or social costs of pollution or waste streams into those value streams. And anytime you can inject additional additional items and include them in those costs, then you get larger swings in costs, and that drives the control, that drives the shifting that you're actually trying to achieve. And it gives people more potential benefit from responding as well. So it's very useful. So we've looked at things, obviously one we looked at was a carbon tax would just be added onto these prices. But there are other kinds of, carbon cap and trade gets even more interesting, because then you do an energy efficiency project in your house, You don't have access to the carbon market, but your utility does. So if you were to trade them the credit that they could earn in the marketplace for the project that you funded, and they give you some money for that, then you just got part of your project financed instead of just on your credit card at Home Depot. So that's, there's good things that can happen if those things are done right. We think about renewable portfolio standards. So places where, for example, in our state, where utilities have certain requirements that they have to meet, efficiency is one way to meet those requirements or part of those requirements. You could see them potentially establishing a market to buy efficiency or other kinds of ways that they could then get credit in a marketplace. And we even thought about things like managing an airshed. So I grew up in LA, so smog up the wazoo, right, back in the 70s. So in Los Angeles, what they would do is start to shut down industry and large, even electricity power plants that were putting out in the airshed. They'd actually run something dirtier as long as it was somewhere else, because the smog was so bad locally. So they would do that with phone calls and, old school stuff. Well, you could make that just seamless and automatic, and you could even start reaching down into consumer level, building level kinds of loads and starting to get them to adjust what they're doing if you were to express, say, airshed values in a smog alert kind of situation. There's a lot of opportunity to bring that into a trading network.
Question over here. By the way, we will accept questions about guitars.
I don't want to be guitars. This is mainly for Rob, but you talked about a lot of different possible ways to move to a low-carbon world. One that I'm interested in is high-voltage DC transmission, where when the wind's blowing here and not there, you don't have an oversupply here and an undersupply there. The larger you've diversified both your sources and your customers, the less you have need of storage. And I'm wondering if that's something that you guys are working on.
We don't have any activity at the laboratory other than some analytic work in that space to try to look at benefits. High voltage DC is going very strong in Europe. So they're looking at high voltage DC underwater transmission network, ringing Europe, linking offshore wind farms, as well as sort of intercontinental or across ocean type transfer, so connecting England to the mainland and connecting North Africa and Turkey and that part of the Middle East to Europe's system as well. So HVDC, high voltage DC, is great. We have I think the first one in the world, the first serious one in the world, runs from Cielo Falls over by the Dalles down to California and works great. So these superhighways for electricity allow you to move power long distances, and for the reasons cited, that can be a real advantage in terms of economics. The question is just one of cost, and the other question is one of siting. So the equivalent of nuclear waste and carbon leaking out of a sequestered hole is the difficulty of trying to site a transmission line of any sort in the United States right now. It is not a done deal that you could do it, even if there was great intent.
HVDC is easier to site because you can put it underwater, and you don't have the fears of electromagnetic radiation. You might have the fears, but they don't have the radiation.
I think the main stumbling block, although underwater is good, but the main stumbling block is just visual. It's just a NIMBY visual impact. So if you put it underground, if we could get underground transmission, then and a superhighway could really squeeze a lot of efficiency out of our grid.
So, do we have time for one more question?
I just like to put it in context, in a social context here. We're really talking about energy problems, energy efficiency, and you're talking about social issues. And I really think that our country has gone very far in terms of educating people in general about efficiencies. And I begin to see more of a global awareness. And so, in a sense, I'm a little more optimistic about where we're going because we have people around the world who are starting to think this is important. So I'm just wondering how you feel. You're right there at some of the edges of this technology. Wondering how you feel about the social context that you're operating in. Are you you showed that wonderful chart of us here not going up but down, and the world going like this. So I'm just wondering, as you look at those challenges, how do you feel about them? Do you feel that that you're not throwing a rock against, a flood coming at you, or do
Is
you
there
feel a little
any
more
hope?
optimistic?
We're doomed. So I think that there's one thought I have in this area actually applies not only to energy, but to a lot of different areas in our lives. And that is one of differing time cycles of response and feedback. So I put my hand on an oven, I feel it, I take my hand off. When we start dumping a bunch of smog into the air, it might take a decade before we notice it, and it might stick around for another 2 decades after we stop. And so that's the one part of this whole equation that makes me slightly worried about where things might be for the next 50 to 100 years. Besides that, I'm actually very hopeful because, like you say, not only here but around the world, people are very aware of the issues. Even China, like I said, they're building a ton of coal power plants, but they know that they need to go green. There's lots of work in other nations to make better, recycling and energy efficient and green technologies that they're going to be exporting to the United States. And at a fundamental level, the price mechanism tells people that, hey, this is costing you something, you need to be more efficient or use less of that. So from all those perspectives, I'm actually reasonably confident that we'll be able to come up with the ways of generating the power and distributing it that we'll need to. It's just a question of, does the time cycle of our ability to build and distribute, will it be able to match the time cycle of our growth of need and the lingering effects of things in the environment?
If I could just quickly add to that, it's as you said, everyone's aware of the problem basically, and there's a lot of people who are very interested in trying to solve the problem. So there's a huge amount of brain power working on it right now, and I think if we don't get any big breakthroughs, then the EIA projections I mentioned will probably be accurate, driven by price. But I'm fairly optimistic that someone will come along with so much brain power on it. I'd like to think someone will come along with game-changing technologies in the next 10 to 20 years that in storage or transmission or other technologies that can really make things cheaper than fossil fuels. And if that can happen, then naturally everything will just become, even in the developing world, they'll just become responsible.
Rob, a final word?
I have two sources of hope. One is that we're doing better than I thought we would be doing at this point 28 years ago when I started at the lab. I was pretty pessimistic at that point that there was much that could be done. I think that, and I hope this is not some sort of American ego here speaking, but the whole world wants to be like Mike. It's pretty evident. Movies, styles, all kinds of things. That may change in the future, China, for example. But nonetheless, we are getting ourselves in a better place, and we just need to really push and get there fast because the rest of the world's they need cheap energy to get their GDPs up and other things, but we got to get them through that long adolescence that we had and into our better place fast, or the world will be in trouble in the next couple generations, I suspect. So that's one reason for hope, is that we're doing better than we thought, and I think we're starting to see the light or show the way. Secondly, there's the opportunity to leapfrog. When you're in the third world, I mean, they didn't put in landlines for phones, they put in cell towers, right? So you may have heard about microgrids. I haven't talked about those a lot today because they don't apply to the US, particularly in my personal opinion. But in third world, in Africa and developing parts of Asia, they're going to be huge. And they'll be heavily renewable. They'll be very intermittent. They may not supply power 24 hours a day to everybody, but people there don't have any power at all, or if they have it, they're maybe lucky to get a couple hours a day. They're used to this notion of rationing and using it when you can and living when you can't. And so if you build with those little kernels of high-tech microgrids that probably have some renewable content and some storage content and some local small generation, possibly with biofuels content, then maybe they can actually link those together into a national power grids in a way that gets them where we're trying to go, again, skipping that long adolescence. That's my second reason for hope.
So I'll conclude with a short war story. About a year and a half ago, I got to go to China for the first time, and we arrived on Saturday afternoon, beautiful March day, did all the tour stuff on Sunday, and I thought, well, I'm going to go running Monday morning at 5 a.m. before there's any traffic out. I was pretty much nauseous after about a half-mile run for the rest of the day. I could smell the burning. It was just something incredible. About 5 o'clock that day, our group was up in about a 5-story building, and you could see maybe 4 or 5 buildings away, and we were told that was a good day. A bad day is when you can't see the building across the street. And what disturbed me is I didn't really see much in the part of the population that they really cared one way or the other. I didn't see any recycling, I didn't see any flow restriction on the water, and that's a big problem. And it reminded me a little bit of the story of the frog in the pot. You keep turning up the temperature, nobody cares until the frog dies. So there's a lot to be worried about. There's a lot of big problems to deal with, but I hope you'll join me in thanking 3 of the guys that are trying to fix it. Great job, guys. Now, I have a 6 a.m. airplane, so I'm leaving, but these guys will be here all night answering your questions if you like. Thank you, everyone. Really great job.